right, well, why don't we get going? So my name is Josh Horton. I'm with Harvard's Solar Geoengineering Research Program. We are very happy today to have Daniele Visioni visiting us. He's Assistant Professor of Earth and Atmospheric Sciences at Cornell University. He's the co-chair of two important initiatives. One is the Geoengineering Model Intercomparison Project, or GeoMIP for short. The other is the World Climate Research Program Lighthouse Activity on Climate Intervention Research, which we're going to hear some about today. I'm anxious to hear about that. So I will turn it over to Daniele.
Thank you. Thank you for having me. Really appreciate it. Yeah, so first of all, now the term that people prefer to use is climate intervention, but I also use solar geoengineering. I think that's much better. But anyway, people like the idea of calling this climate intervention more, so that's what I used. So the thing I'd like to talk to you about is sort of this idea of a robust assessment of something like stratospheric aerosol intervention, SAI, essentially. And the thing that I'd like to do today is sort of three steps. The first one actually, yes, is to give an overview sort of on the international environment side, as in why are people, who is talking about an assessment, why are they talking about an assessment, what do they mean by an assessment? Then give you an idea of at least what I think are the bases we can start an assessment from, and then reconnect the two and say, well, but what could we actually do to move towards a robust assessment? And what do we mean by robust? What do I think that robust means? So, I'm going to be super brief with the overview. SRM, climate intervention, I will use these terms interchangeably because I always forget which one I should use. Deliberate modification of Earth's climate, deliberate being the key word, the difference between other things, the reason why people sometimes decide to include or not include carbon dioxide removal into climate intervention. But in general, SRM, the idea that we observe the problem with climate change being about fundamentally the energy balance, increased atmospheric capacity due to more CO2. Can we rebalance or prevent further imbalances of the energy imbalance through a reflection of solar radiation, so affecting the left side of the normal energy balance equation one learns about in climate dynamics. To reduce some of the risk, the other key is to reduce some of the risk produced by global warming. And in particular, I'm just going to focus on SAI, stratospheric aerosol injection. I will also acknowledge that I will mostly talk about sulfate because that's what I've done for most of my career. But of course, there could be also other material in the stratosphere. For some of them, the discussion would be similar. For some of them, the discussion would be different. Essentially, the idea being, well, nobody lives in the stratosphere. Lifetimes of aerosol in the stratosphere are much higher than in the troposphere. So the load that you would need to, the amount you would need to inject to have a load that reflects solar radiation is sometimes 100 times lower than the one it would be in the troposphere. So there are clear, easier trade-offs. And the essential observation is that what volcanic eruptions did. The last one being Pinatubo, Hunga Tonga sort of tried but didn't get anywhere close. But in general, so we have that observation. We know that a volcanic eruption, if it's sulfur rich, gets to the stratosphere, cools the planet but for a couple of years, so we know in a way it would work. Now, people have been talking about SAI now for a while, since the early 2000s. Paul Crutzen had a famous paper in 2006. But I would say that in the last 12 months, roughly, there have been a lot of steps. I feel like there clearly is I think it's undeniable that there's a momentum building. That doesn't mean all sort of in favor of talking more about SRM, but there's clearly more and more interest to discuss it in many places. So I would say the first thing, UNEP, the United Nations Environmental Program, had this report that they did not call an assessment, that they don't even call a report. They called it an independent expert review of SRM research and deployment. The independent, because they actually wanted to pretend this was not a UNEP thing, because they maybe didn't have a full mandate to have a full report. So they asked a bunch of guys and people, well, I think Kate Ricky was the only woman. They asked a bunch of people to have this expert review. So it's a pretty short, sort of Q&A based assessment. It does say I think it's a pretty balanced report, which actually was part of the problem and why many people didn't like it. But it did say something in a way very important. Modeling studies have consistently shown that climate change the climatic changes in the earlier region are much smaller with a carefully designed SRM deployment than in a world with continued climate change. This is, I think, having these in words is actually pretty important, but some of the ways in which this was kind of, who is this from, who is this for, kind of overshadowed maybe, I think, the importance of having something like that in paper. So this was an expert review, it was not an assessment in many ways. Following that, the World Climate Research Program that is much more, unlike UNEP, whose representatives are sort of nominated by states, the World Climate Research Program is much more of a bottom-up, climate scientists driven organization, but it has been very influential in the past when it came to highlight research directions. For instance, they were very influential to study more the variability of ENSO, climate modeling. They were very influential. Plus, they work together with the XCC in many ways. So they had this Kigali declaration. It came from a meeting that happened the summer before that was signed by all the attendees, the Climate Science for a Sustainable Future, where they did talk about climate intervention as well. There was mention of climate intervention and the fact that the WCRP wanted to position itself as an impartial arbiter around the topic of climate intervention in general, so SRM and CDR. For this, they launched this Lighthouse activity that I've been asked to chair. Essentially, the Lighthouse activity, someone says, well, a lighthouse is something you have so to not have the ship wreck. But the other way would be, imagining a lighthouse as a shining light to guide people to a safe haven. But in general, it's assumed to be sort of a non-permanent, but overall around 10 years program to coordinate other WCRP programs and rapidly advance science in some specific areas. So what the actual WCRP Joint Steering Committee is pretty robust and international road, and then what we sort of approved in what we're supposed to do is the acknowledgement that a comprehensive assessment is needed. Many are needed to inform climate policy, also when to do with CDR. And that we would like this Lighthouse activity to ensure that research can be conducted transparently with open access results and to model, but also that scientists globally can be involved in the research, and in also defining a metrics of relevance for assessing what is safe or not and what are the risks and benefits. And I will tell you, there was a lot of fighting over adding the word benefits to these, because a lot of people just wanted to, even in the Joint Steering Committee, wanted to just say the climate risks of climate intervention approaches. So there's a lot of these push going back and forth. Finally, well, not finally, but at the there was a meeting of the United Nations Environmental Agency. It was back in February. Now, this is a meeting where there are country representatives, not that many scientists, even though there are the major groups that represent indigenous groups and science and technology and so on. Where Switzerland, for the second time, the first one was during or right before the pandemic, tried to push for having an assessment done by UNEP. The words they used was an ad hoc group of experts to produce a detailed assessment report. Immediately, a big fight ensued. There were a lot of different interpretations of what a group of experts mean. Who is an expert? Who is an expert when it comes to SRM? Who decides who the experts are? What is in a detailed assessment report? So discussions immediately moved to some countries, especially African countries, discussing about the idea of a moratorium following the Convention of Biological Diversity. It is the only one that actually officially talks about geoengineering. Some other countries said, well, the WCRP has just created this Lighthouse activity. Those are the people who should do the assessment because they're climate scientists, they have the expertise. Some other people took this very badly because they said, no, an assessment is not just about climate scientists. Even if you think of the IPCC, there's a lot of working group 2 and working group 3 expertise that has to do with the social scientists and environmental impacts and so on. A lot of the usual discussions about moral hazard. Countries like Brazil and countries in South America pointed out that maybe the research is not inclusive, that they don't know how to access. It was an interesting thing also as the chair of the Geoengineering Model Comparison Project. The data is all public, but it doesn't mean that it's perceived as being accessible everywhere in the world. and I understand that it's pretty hard to actually go on the Earth System Grid and download climate data. And so there was a discussion of we can't have an assessment unless we've had the capacity building. Eventually, on the last day, there was this idea put forward of having sort of a research repository as a starting point for discussion. Then there were discussion about what constitutes research for this purpose. People were like, only climate research, also legal, also ethical. So there was a lot of this. Eventually, at the end, nothing happened. There was no agreement whatsoever. But I think the fact that they discussed this for so long is actually a great point, a great step. And the next UNEA meeting that is going to be next December, so in 2020, the end of 2025, I think is going to be, depending on what I think we do in the next, now less than 18 months, I think that we can really have hopefully get better at this kind of discussion and maybe decide something. Now, the last thing I would say is that, well, there's also the 7th assessment report from the IPCC coming up. The scoping meeting is going to be in Kigali in December, where the actual contents of the chapter is going to be decided and the bullet point of all the 3 working groups. For the very first time, SRM is explicitly named in the cross-cutting areas in which they want an expertise. I know that there's clearly movement, albeit at the scoping meeting in December, and I know that there's a lot of movement and people starting to think, should we have a chapter in AR7 that explicitly talks about SRM? In which working group would it be? Can we come up with a cross-working group chapter? A lot of those discussions, but again, there's a lot of this going on, right? So people are starting to move towards the idea of having an assessment. And I think it's incredibly positive. My personal stance is that whatever we're going to decide about SRM, none of us in this room is going to be the person making the decision, but what I hope is that there is more information so that whatever decision gets made, it can be informed. The worst case scenario to me is making a decision while being uninformed. So I am working hard towards thinking about what an assessment would mean. But there are a lot of issues, right? So, and again, as I said, there's a lot of fuss, I would say, over an assessment. What is the point of an assessment? Why is this idea that climate science has to have these constant list of assessments when no other field of science does in a way? What kind of research goes into one? Should an assessment precede governance effort or come before it? People were at the UNEA meeting said, no, there should be governance first, but how do you govern something you don't know and that you have no agreement at the broader international level? That's sort of what the IPCC is for. Who does the assessment and then what happens after the assessment, right? Do you reevaluate after a while? Is there a point where you say, no, let's not do it, or yes, let's do it, let's research more? Right, so what is the point? So, well, I think the good place to start is say, well, what do we know about SAI? And the point that I will take is that even at the IPCC side, the physics behind climate change has been known, I would say, for a whole century, if not more. But people felt that there was the need to lay the basis of saying, well, since it's hard when the IPCC started, it was hard to observe it actually in many ways. I think people thought it was useful to have an agreed upon definition of what it was or what the risks could be. So let's try to do something like this for SAI as well. So what do we know? Well, I would say that it's clear, this is for SO2, but it's clear that if we put SO2 in the stratosphere, aerosols will form. And we've seen it even with Pinatubo, that was over 20 teragrams of SO2, that the aerosols would be at the size that we expect it to be, so around 0.2 to 0.7 microns, even if we dump it all at once, which is not what SAI would do. We know that they would produce H2SO4 vapors. We understand that theory very well. We understand that then the aerosols would have competing nucleation, condensation, coagulation processes. If there are already particles, the H2SO4 vapors maybe favor condensation over it, which means that the particles grow bigger. But we know that, right? And the fact that we know something doesn't mean that there are no uncertainties. But I think sometimes people will be like, how do you know it would work? Well, we just do in this sense. I would say that the point, we also understand very well, in a way, the radiative processes that would happen after this. So these figures from John's paper, I actually just removed, there are 20 different lines for 20 different materials, I think. But when I was going through this, I tried to just isolate the one, right? So we know that then the aerosols are of that size. This is for a distribution of 0.3 micron. They reflect sunlight, cooling the planet. This is on the x-axis, you see the wavelength of light, so the solar spectrum looks like that as the blue curve. On the y-axis, you see the real refractive index, so the part that regulates scattering. In a way, we know that it does, right? If the particles are smaller, it reflects maybe a little bit differently. If the particles are larger, or that. But we know this is not a climate model. This is, in a way, a radiative transfer model. This is actual robust understanding of the theory, I would argue. So we know that if the aerosols are there, they would reflect sunlight, and that would shift the energy balance and cool the planet. Now, it doesn't mean that the aerosols are completely inert, especially if we're talking about sulfate. We also know that, this is the equation sort of on the energy balance, and say, well, S0 is the incoming sunlight at the surface. If we reduce that one, we reduce absorbed sunlight, that shifts surface temperature. We know that works. We also know that aerosols will interact in other ways. We can say we don't know all of them, but actually I would argue that Pinatubo, again, gives us an upper bound for things that can happen in the stratosphere. This is, again, from John's paper, and the imaginary refractive index. So the part that regulates absorption. Aerosols clearly, even at 0.3 micron, absorb a part of the solar spectrum, which means they warm locally. This warms the air, produces a temperature perturbation in the stratosphere. That is one of the interactions. We know that the aerosols would interact chemically because they offer the acidic H2SO4 particles offer surface area for heterogeneous chemistry that would affect ozone. All of these things are things we know. Again, that doesn't mean that there are no uncertainties that we know. And these curves you can find for any other material you might want. We also know that the aerosols would not stay there forever. They will be transported depending on where you put them, and they will eventually fall. So there are many examples of these. This is sort of a figure from a very, very early paper now, 8 years ago. We know that if you put aerosols in the tropical pipe, what we call at the equator or close by, there is both going to be the large-scale Beer-Dobson circulation pushing them up. There's also going to be a self-lofting through localized heating, if this is sulfate with absorption we're talking about, so the aerosols, we know they will stay there. We know that the tropical pipe produces a strong confinement there, so air stays there, but eventually the Beer-Dobson circulation moves things at higher latitude, so we know that. And we know that eventually that fate is that both through large-scale stratospheric circulation and maybe even surf mixing and other processes, and through gravitational settling, because these particles have a specific weight, eventually the particles will leave. We know that they will not stay forever. We know that this is not a Snowpiercer kind of situation, because we know that the aerosols eventually leave after a couple of years. We've seen with Pinatubo. Maybe black carbon could stay more because the self-lofting is much higher, but we know that they will leave. And then we know, I would say, we don't know everything about the Beer-Dobson circulation, but we know climatologically where it goes, and so we know that if we put aerosols at 30 north, they're not all going to 90 south, never. They're just going they're going poleward, mostly and on average. So these are, I would say, things we know and that they're robust enough for us to tell. Of course, again, these still means that there are uncertainties. And here's the sort of my idea of four main natural science kind of, physical science kind of questions, and then sort of the last one that I think though is important. What scale would be needed to reduce global temperatures? What side effects, so how much stuff do you need to put in the stratosphere to get a certain amount of cooling? What side effects would all of this stuff have? And I divide here between side effects, imagining all of the direct interactions that these might have, even at the environmental side when the aerosol fall down, and then what would the regional surface climate impacts be, as in how would climatic patterns change? And then, since this is not a monolith, this is not going down and turning down the solar constant in many ways, are there ways in which we could do these that could minimize the harm of all the other things? And then, when we talk about all of these questions, how would SAI and how would all of these questions be understood? How would SAI be used, perceived? So when the key word in the UNEP expert review was a judicious, responsible deployment, uniform deployment of SAI, well, that's not necessarily the way things go. So that's important. And how will all of this be discussed and perceived? The thing that makes all of these complicated is that all of these questions are connected to one another. I'll give you a few examples. The more, in this case, sulfate you put in the stratosphere, in a way the larger the perturbation is going to be. If the sensitivity to these aerosols is higher, and so a small amount of aerosols cool more, you need less. That's in a way good. If you need much more, well, the perturbation is going to be larger. So this, in a way, is the equivalent of what we call climate sensitivity for climate change, right? So this is an example of GeoMIP results. These are 6 models that all try to cool the planet. It's I'll just zoom in on a model, but to say that many models did that. The idea behind this experiment, it was decided in 2014, was, well, let's be under SSP 585 emissions, and let's see if we can either turn down the solar constant or put aerosols in the stratosphere to reduce temperatures to the same one that would be under SSP 245. So we have sort of 3 different comparisons we can do. SSP 585 with SSP 245, and then SSP 245 with the 2 different geoengineering experiments. The sort of first observation is that, well, if the question was, can we cool the planet? The answer is yes. From this figure only, you could just get the takeaway of like, yeah, it works, good, let's go out and do it. Of course, that's not as easy, right? A combination of the fact that you have different climate sensitivity in the model, leading to different amounts of warming, and you have a different sensitivity to the aerosols, mean that the aerosols are good, that you're going to need different aerosol optical depth in the stratosphere to achieve the target that you set out to do. And in this case, this is going to be combined with the fact that the aerosols are going to have different size distributions in the models. And then this means that the warming that will be produced in the stratosphere will be different. And here, this figure we had in a paper and that we had in the ozone assessment that we wrote in 2022, it's interesting to see that even for an optical depth of 0.1, so a reduction of roughly 1% of solar reduction, the amount of heating that the models project can go from as low as 1 Kelvin to as high as 4 Kelvin for the German model. And if you go to higher optical depths, like 0.3, which is a huge amount, you can go anywhere from 4 to 10. So that's huge, that's large. It is a pretty large experiment, right? So, and this is a connection between not just the stratosphere, but a connection between the climate sensitivity that the different models have and the response to these aerosols. Another example, right? How do eventually the stratospheric changes couple with changes in surface climate? If what we care about is precipitation, there is this coupling. And when I was at the last Spark meeting, I was telling everyone, like, look, you always try to argue that climate change, we should also care about the stratospheric coupling. Yeah, there's no better coupling than under SAI, right? If you want to argue that the QBO is important, come do that with SAI, because it's actually, the signal is much better, and we don't have to, there's actually a lot of interesting things that we can do. So still going to the same GeoMIP models, the models were asked to do the injection all in the same way, which it was injecting between 10 north and 10 south. Well, here's the distribution of the optical depth in the different models. It is clear that there's a large difference in how the models spread these aerosols. UKSM, the UK model, essentially sees that all of the aerosols stay in their tropical pipe. The French model, CNRM, essentially has a pretty even spread. And that's just on the aerosol side. If we go look at the amount of SO2 that you need to get those aerosols, those are also very different. Like UKSM needs 21 teragrams by the end of the century. The other French model, IPSL, needs twice as much, 40. That's a big difference. And this eventually does affect surface climate, right? So here's the power of having those 3 comparisons, right? So on top, on the left here, you see just global mean surface temperatures in the last 2 decades. Top left, this is just warming from the different models, over 3 degrees, 2.5 degrees warming more between 585 and 245. Then on the middle left, you see the experiment with actual sulfur. What do you see here with a different temperature scale is that there is some consistent residual warming at high latitudes. And then below you see what happens if we just turn down the solar constant. There is almost no residual at all. Now on the right, what you see is as a metric of sort of model agreement and disagreement, I used multimodal standard error here. And essentially this is saying that, well, even under climate change, there is a pretty high degree of uncertainty over how much warming there will be. Most of that is for the polar amplification, but there's also a lot of uncertainty over Africa because we know it's an area where climate models actually don't do great when it comes to surface climate. We can see the same for G604. Actually, I would say the intermodal spread seems lower, which for surface temperature shouldn't be a surprise. We are preventing further imbalance, so makes sense that this is more coherent. But there are still areas of disagreement. Over Antarctica, over the high latitudes. Well, this disagreement is also much, much smaller when it comes to just turning down the sun. So in a way, there is a part of the uncertainty that is driven by the stratosphere. Of course, one of the main things here is the fact that the models have such different latitudinal distributions of the optical depth that, of course, UKSM is going to cool more in the tropics than it does at high latitudes. There's no aerosols at high latitudes, so the sun is going to keep shining the whole summer. So, of course, there's these uncertainties. And the question then could be, well, how do we reduce them in many ways? And then again, the final thing is that, well, if we fundamentally care about these regional surface impacts, can we think of injection strategies? So can we use the bird-Doppler circulation to have different latitudes of injection and try to minimize the impacts that we saw in the figure before? On the figure before, it was kind of like what we knew at the time, what they knew at the time. I wasn't there, I was involved. Not my idea, that experiment. But can you do different injection strategies that would minimize these impacts? So for this, I would say what we tried to do was figure out, well, let's try to do that, right? This is kind of the equivalent of what people have been doing with green functions when it comes to understanding climate sensitivity, and say, let's try to inject the aerosols at different locations in different models and try to understand, is the model spread depending on that? It turns out it is, and injecting the tropical path is the worst possible idea ever for many reasons, but also because the tropical stratospheric circulation is the worst, has the highest spread. But what I tried to do here was sort of breaking down the problem in two. How much SO2 is needed to produce a certain optical depth is a different problem in a way that what is the overall distribution? Because if UKSM just needs twice as much aerosols, that's fine. In the model, we can just put twice as much aerosols. But if the pattern is different, it means that to obtain the same change in energy balance, then we need to inject in different places. So we did that. We went for temperature. The interesting in a way, at the beginning, surprising thing was the fact that when it comes to temperature and precipitation, there are sort of robust patterns of course, if you put stuff in the northern hemisphere, you cool the northern hemisphere more. You shift the ITCZ in one way. If you put it in the southern hemisphere, you sort of do the same. So you can sort of approach this problem as a combinatorial problem and say, can we inject aerosols in different places to avoid residual changes? So I tried to do this, well, I've been doing this for a long while, but this is sort of, we tried to do this again with CSM and then having it replicated with other models. What you see here is a much more moderate scenario, so just SSP245 and saying, can we use these the multiple injection locations to actually minimize changes and keep things at 1.5 above pre-industrial. So the actual cooling would be 0.8 Celsius. This is what you see there. But then if you look, this is a large ensemble. If you look at the statistical changes, they're essentially just something going on with the AMOC in CSM. So not super great, but it actually points out the fact that based on the results of this climate model, if you were to do these objective-driven SAI strategy, you would essentially cool back down to prevent temperatures from going above 1.5 with essentially no surface changes in temperature. The other thing we did though was say, well, of course, but that depends on the magnitude of the cooling you're trying to do. So in this set of simulations, I also tried to say, well, what if we want to cool, why 1.5? It's a number we sort of made up. No, it's robust, but also it's just a number. What if people wanted to cool more? So to 1.0, what if they wanted to cool even more? Clearly what we find is that, yeah, of course, the temperature looks worse, even just compared to the past period when that temperature was like that. And of course, you have more areas, the signal starts to emerge. You're increasing your signal, so your signal to noise ratio goes down, goes up. And so you can start seeing that there are some differences. You can see it's something in the Pacific. You can see some residual winter warming over Eurasia that is kind of unavoidable because it comes from long wave processes out of CO2. So this was the way we went. Now, though, if you go this way, there's kind of a big trap, which is that the problem starts to become untreatable. If you start asking yourself, well, what emission scenario are you using? Under which, what's your temperature target? When are you starting? It turns out to be very important for ozone. Where are you injecting? What if there's a termination? What if there's an interruption? You can essentially, we don't have infinite computer time in our climate models, and that's probably good because otherwise we would just waste all of our day doing that. So there's clearly a problem that becomes multidimensional and quickly becomes intractable, and in a way hides the other question that I haven't asked, which is, of all of the questions we asked before, how wrong can we be if we use all of our brain power and computational power to just come up with millions of scenarios and solve them in the climate model, or also maybe ignoring the sort of more scientific question, which is, of all of the questions that I asked before and the things I showed, what if every model we have is wrong? How can we tell that part, right? And again, all of these, it all eventually connects to the last question, right? How will SAI be perceived and used will depend on all of these questions, but also on how much, in a way, we trust the science. So, what is the final goal, and how does this get close to an assessment? Well, I'll point out this figure from AR6. There's a lot of stuff here. So on the left, you see the different SSPs, the different various emission scenarios, pointing out to the fact that we know that every emission scenario, except the ones where we make up a lot of CDR that we don't know whether it's going to be feasible, will lead us to more warming, that there's going to be uncertainty associated with the warming that depends on the climate response. But that essentially, the part on the right, which is the one I like, is the one that sort of says, the main point behind this, nobody lives in the global mean. The global mean is just a signal of increasing energy imbalance, I would say. And so increased threats and risks in a variety of ecosystems and different systems. Weather events, distribution of impacts, ecosystems, you can make a lot of them. And this figure says that not all of these impacts are going to be linear with more warming, which I think is important. Not for all of them we have the same confidence level. So when there's 1 dot, it means low confidence level, 3 dots, high confidence levels. And in general, a figure like this is incredibly robust. But then you would ask, well, what's the basis of this? And I would say that the reason why people or policymakers would trust this figure is because it comes out of a process like the IPCC one that includes lots of scientists from all over the world, collecting research from all over the world, having it agreed upon at UNFCCC meeting. I think that all of these carries on with its power that speaks to the robustness of the process that has been created, and eventually means that we can show this figure and people are not necessarily going to question, how did you calculate the RFC4? There's clearly a lot of science going on behind this, but this is an important way to sort of summarize everything. To me, an assessment is something where you can come up with something like this and have it essentially perceived as trustworthy. And then people can act upon this. This doesn't mean, the fact that this figure exists doesn't mean that people are magically reducing their emissions, but it does mean that there is a generally agreed upon understanding that climate change in the future will be that. The other word, I will just say, I use the word robust assessment. So what do I mean, what do I think when I say robust? So in the words of Elizabeth Lloyd, who wrote these words in 2010 when there was a lot of discussion over actually how robust are climate models. This paper is sort of a defense of climate models and pointing out all of the ways in which we understand them to be robust. But essentially the point she makes is that model robustness and robustness of an assessment is not a scientific thing. There isn't a scientific equation that tells you how much something is robust. It is a societal process. Models accrue credit and trustworthiness upon being supported by empirical evidence and theoretical derivation. If there is trust, then an assessment can be perceived as robust. So what steps can we do for that? Well, I try to break down the problem in this and sort of show you some areas that I think are very promising. Well, I'm working on, but a lot of other very great people are working on, and I think will help. So one, as Elizabeth Lloyd said, having more process-based understanding and climate model improvement, which I think go hand in hand. Of course, for this the point is we have one big experiment, which was Pinatubo in the past. So working even more to understand how aerosol microphysics in the aftermath of something like Pinatubo happens in models. Why are the models different here? There's a lot of stuff. This was a large paper that we wrote, took a couple of years. The observations are also not great for Pinatubo in many cases. So there's large uncertainty bars. How do we reconcile this? How do we understand this? And for a lot of this is also, we go and try to understand better the aerosol microphysics and the assumption in the aerosol modules inside the climate models. So one thing that I'm getting sort of excited about is sort of the idea, these exist already for a lot of things related to surface climate, which is sort of producing a model ranking, a model evaluation that tells you whether you can identify some emergent constraints and actually tell you this model is actually just out too large, it's just not to be trusted, or this model can be trusted more. Now this is delicate, but I think it can be done. So one thing that we're working on is sort of trying to do this, having this model ranking based on various metrics, trying to collect a lot of them, and figuring out whether we can say something. And I think this told us, this is sort of very preliminary, but I think it told us something interesting. So here I have 4 metrics. Optical depth, that tells us about the energy balance. Stratospheric burden, that sort of tells us about lifetime. And then effective radius, this is after Pinatubo, that kind of tells us about microphysics. The interesting thing is that just like for climate projection of climate change, people tune the model to get historical warming and total atmosphere balance right. But when you tune there are different tuning philosophies leading to differences. I'm sure I know because I've done some of these simulations, but it's clear that people tune their models for something like Pinatubo differently. And so understanding how this tuning happens to get what right, these figures kind of shows that. There are models that have a very good optical depth compared to observations, while having a pretty terrible stratospheric burden, which means that they get optical depth right, but lifetime wrong. What does that tell us maybe about the circulation? Same thing, the models that get optical depth right, most of the times get effective radius right, so there seem to be actually weird differences that we're trying to understand between burden. How can you get the burden right, but not the effective radius right? This speaks to what exactly gets tuned and how the microphysics work in the model. So this way of ranking, this is not to say your model is good, your model is bad, but more to say, here's how your model is behaving across this large set of metrics. Let's try to figure out how we can improve them all. And I think this kind of goes to the question of robustness.
Can I ask a question?
Yes, absolutely.
Just about this, because my concern is you say that we know Pinatubo.
Mm-hmm.
My sense is we actually don't know Pinatubo terribly well at all. Pinatubo came in the midst of a transition from an El Nino to a La Nina, and it's not obvious to me how much of the cooling, if you look at the time series of temperature, how much of the cooling associated with Pinatubo, I mean, what is clear to me is that through the 20th century, climate models use volcanic forcing to compensate for their lack of internal variability in the model. They don't get a very good El Nino, they don't get a good PDO, and therefore they compensate by using volcanoes. And therefore my concern is that all of these models still don't have a good El Nino. The CMIP6 still have a lousy El Nino. They don't get the tropical Pacific right. And therefore, when they calibrate on Pinatubo, I actually think if they've gotten El Nino wrong, the whole thing is in error. And that is, you may be ranking between them, but they're all systematically in error.
So I think that is a great point. I will say that actually though here I am only showing stratospheric metrics. From actually most of these models don't even have a coupled ocean in this case. These are most AMIP simulations. Here, this was part of this new project that we're trying to put together and get funding for, and this is the stratospheric part. So here, I don't necessarily care yet about the climatic impact. Here I care, do the models get the stratosphere right? Now, for the surface, you're absolutely right. So the other question I'm trying to sort of reconcile is, how do we measure whether the models are cooling correctly after Pinatubo? Do they get that kind of signal right? There's clearly the usual, people say Pinatubo cooled by alpha degree, not that high. That's clearly wrong, but on the other hand, there's other estimations like the Candy et al. 2012, where they say actually the cooling was only 0.12 Celsius. Well, I think that that's a bit too low, but I think that that's a great paper, trying to replicate those analyses in CMIP6 and also using other methods to try to understand. Now there's a lot of, I'll use the bad words, there's a lot of machine learning methods that have been used to understand, for instance, sensitivity of tropospheric aerosols in climate models. So my question is, can we do the same for stratospheric aerosols? Can we understand a little bit better how this coupling works? If you don't get the stratosphere right, it's gonna make it even harder to figure out whether you're getting the surface response right? So this is just a metric to evaluate whether the models are doing things good in the stratosphere, but only 2 CMIP6 models had the fully coupled stratosphere-tropospheric. The other part of the question is, can we do the same to figure out whether models are cooling correctly after Pinatubo and whether they're getting the things we care about right? I think that's, I don't know the answer to that, but I'm trying to figure it out.
I just feel like if any country or or consortium of countries ever implements a solar geoengineering scheme and launches aerosols into the stratosphere, there will be a fundamental uncertainty on what the real world response will be, which is probably a factor of 2 or 3. And I don't see any model results narrowing that in the next 50 years.
I agree, but also I will say something that I think maybe is contention and say I don't necessarily care at this point, as in if let's say that we are in a point where countries are going to decide to do this, they're not going to launch a Pinatubo in one day. They're going to go with the first plane, go up, put a ton, maybe. This is not an experiment, I'm talking about day 1 of deployment. Then we need to figure out what do we measure on day 1, week 1, month 1, year 1, to figure out whether our models are completely out to launch. And at that point, essentially, this becomes a question of detection and attribution. Our models are not ready to do that, I agree. But also I think this is really like hard to find a way to convey it properly, but to say, this is not our problem, this is not my problem for now. I'm trying to figure out, we don't need to predict what the climate response will be after 50 years of cooling yet. That is not the kind of question you need a precise answer to, just like you don't need to know if the climate sensitivity is 3 or 5 if you're trying to decide whether your emission mitigation policies have to be more or less stringent, right? You assume that there's gonna be risks and you behave on those, but I think that we can do something here even if there's a fundamental unknowability that I think goes down with SRM in many cases with respect to climate change, because more warming is going to lead to further imbalances and instabilities that will not happen under SRM, but fair point. I'll be happy to talk more. I'll just conclude briefly then. So the other part, as I said, how do you do this scenario exploration that people really like doing, this strategies exploration without overwhelming everyone with millions and millions of simulations? So one thing that we've been working on is to develop sort of climate emulators, just like En-ROADS has been sort of fundamental to get people to talk for the Paris Agreement in a way, I would say. Can we do the same through have people explore and think about SRM, extrapolating and from available modeling to understand uncertainty, to understand what would happen. So we have a couple of things going on, none of them sort of the public stage yet, but I think this is a web-based tool based on the best modeling we can do, all of the information that we have, to sort of people that say, look, just look it up for yourself. This is what our models are telling us. But now I have to say, a few countries said outright falsehood about what SRM would do, like SRM would cool the Arctic more than under climate change. No, that's not physically possible, it's also untrue. But in a way, that is because part of the research is impenetrable to this kind of policy discussions. Can this be helped by having a web-based transparent tool like that? Maybe. I've been very conflicted about this, but I think I've landed on the fact that I think would be useful. Of course, in that case, we are not allowing people to also toy with injection locations and stuff. On the more scientific side, we've developed this methodology through the sort of Green's function of SAI deployments to sort of say, can we let an emulator that combines different injection location to explore suboptimal scenarios? This is one example. This is something my grad student has been working on. Is first paper was just about sort of understanding termination, interruption. In this case, we're sort of saying, what if there are different countries with different goals and these goals don't match because maybe they don't talk to each other? What would happen to surface temperatures if they were injecting at different location? On the top left, you can see different actors doing different injection, not necessarily being very smart about them. We don't care here. What happens to global temperatures? What happens to surface temperatures? Again, a tool like this will always be sort of have a huge problem being that it's hard to represent uncertainties in a place like this, and it does collapse a lot of uncertainties. But I think the methodology is robust, is similar to a lot of the climate change emulators. And so these, I think, could help people also have the discussion about what if the SAI deployment was suboptimal? Well, now we might understand it a little bit better. Final thing, and that again, I think it's super important, is the fact that this research has to be international, or it won't be. It will be a mess. I've been working a lot with the Degrees Initiative that Andy Parker, who was here when he funded it, has been working on tirelessly for 10 years, working with scientists in developing countries to do their own research about SRM. I've been having a lot of fun working with them. It's been great. Through Geoengineering, we've been doing a lot of stuff. But it is true that one of the main things they lack is access to actual climate data, because it's terabytes of data they might just not have the capacity to download. It's a huge actual material problem. So a thing that I'm trying to gain support for is to sort of say, can we have a cloud-based research product that would allow people to just download the data that they need without having to go to the Earth System Grid and download the whole CMIP6 archive? Can we maybe try to downscale the projection we have? I would not trust the downscaling that comes out of our projections, but I want to know how it works. What are the things we don't know to do a better I feel like there is a sort of pitfall of, we don't know this, so maybe we shouldn't do this, as opposed to, well, let's try to say the best we can and then figure out from there what do we need to do to have better projection. But this does go, in my mind, through making sure that this data is more available and that it hits a bit closer to home to what people care about. So, and that's the concluding slide. I think that all of these things, sorry, you're not supposed to actually follow this. This is just my musing, but it's sort of say everything is connected. Climate model improvement does not sit in a vacuum. Outdoor experiments or lab experiments also, I don't think they sit in a vacuum. I think they make sense, imagining them as increasing our process level understanding, improving observation, that eventually lead to more robust climate model improvement, that lead to better projections, that help us understand intermodal spread. But these multimodal projections are only useful as input for having people, telling people this is the potential risks and uncertainty bars of this thing you care about, whether it's monsoonal circulation in India or crops in Africa. That is an important thing. That eventually all of these, as we grow as a community and as we keep having this positive feedback loop, I would say, we also understand better potential scenarios and strategies to use and simulate. And so this is not something you do once. I imagine this as sort of a positive feedback loop where we do this, but eventually does lead us to a point where every loop has us more informed than the past. But to me, the only way we go through a robust assessment is by having all of these gears turning all at once. And that's all for me. I hope this was food for thought. Thank you.
Thanks, Daniele. So, questions and or comments? I imagine there are quite a few, so just get going. Back there?
Thanks for the talk. You motivated the case for intervention with that plot from the IPCC that showed the risks of different human impacts. You know which plot I'm talking about? It's the color bars. Okay. And so that plot is with low or no adaptation. And I've tried to look for the corresponding plot in the IPCC report that actually has adaptation in it, and I can't find it. I'm not trying to pick on you. I'm just trying to say, as a field in our discourse, do we maybe give too little stock and too little investment and too little assessment to the role of adaptation, such that it motivates extreme solutions like the ones you're proposing?
I think that's an absolute excellent question. The AR6 actually had a whole chapter on the concept of maladaptation, and this idea that essentially a lot of people are seeing the fact that adaptation is actually not going as great as we hoped, as in people end up using money to build gigantic seawalls that cost trillions of dollars. I'm not saying adaptation is bad. Of course adaptation has to happen, but I don't think, just like I don't think we can rely on CDR necessarily that it's going to scale up, I also don't think we could necessarily rely on adaptation always overcoming the current changes compared to future changes. Just as I don't think we should rely on SRM. I don't think we need to rely on any single thing. I think that it's better to hope for the best and prepare for the worst, and so do all of the things at the same time. And of course, there is a challenge. I work a bit with people that do fishery modeling, and they have a long discussion of, should we have more or less exploitation in the future? Should we have managing practices that prevent this? At one point, when you do modeling, you have to sort of have a, all else being equal, this is how risks are going to change. And I really think that there start to be plenty of examples in the literature of examples of maladaptation, essentially showing that people and institutions end up throwing their weight behind poorly reasoned adaptation measure. You could consider SRM in it. Sure, that's your prerogative. I would say that though what we're seeing is that people are spending way more money that would be needed for SRM on things like, again, maladaptation measures, and so that it does make sense to think of this and to report on this in the idea that maybe adaptation is just not going to cut it to prevent risks. How do you prevent heat waves of 8 degrees over the Pacific Northwest? What kind of adaptation do you need to do? You need to put everyone in a stadium with air conditioning for 3 days? Maybe you can, but is this the best way? I think this is a discussion we should absolutely be having, and I agree with you that adaptation is still, in some circles, thought of as the same way Al Gore thought about it in the early 2000s, which is we shouldn't talk about adaptation, we should just push people to mitigate. But that's where we are, we need everything.
Just a brief comment, which is, you're right, the chapter is about maladaptation, it's not about adaptation, and that in itself is very telling. Right? I mean, obviously as humans we've profoundly adapted to the climate, and the heat or cooling I'm feeling right now is the main story. The footnote is where we make mistakes and maladapt. But to make that the chapter is speaking to this problem.
Anybody? Yeah.
And Josh, you
call
pick.
right over here then. All right.
Thanks for a very interesting, informative talk. At the end of your talk, you mentioned about monsoon in India and crop in Africa. So now, this is a theoretical question. If there is any such a cooling effect, will it reverse any of the changes that is taking place in biological diversity? As of now, I'm from plant biology side, wherein the cool climate adapted plants are migrating towards the upper latitude, and warm climate adapted plants are migrating towards further. So do you think theoretically whether there will be a reverse in the change?
Great question, and I would say, so these climate scientists sometimes are accused of having carbon tunnel vision, which is to just think about global warming while there's a lot of other crises, and those crises are going to exist. And most of them are actually depending on things that are not necessarily have to do with directly climate change, but maybe they have to do with nitrogen pollution and all of that. But on the other hand, I think the U.S. is a clear example of the fact that the beetle that feeds on the bark of trees is partially driven by temperatures not going as cold as they would, and so they can spread a lot further. And there's also a lot of suggestions of the fact that maybe trees are in areas where they wouldn't have necessarily been, right? It's sort of zombie trees that exist in areas where actually the conditions are not ripe anymore. So it is clear that it's only a part of the equation, but that preventing further increases in temperatures would in part aid with biodiversity. On the other hand, if you try to cool too fast, you could have the opposite of, one thing I haven't talked about is, of course, and if you're doing something like this, then the main reason why you have to keep doing it until you drone carbon back down is because if you stop, then your temperature just shoot back up. And that would be way more, so the sort of termination shock risk is clearly a point where we're committing to something that has the risk that if we stop doing it, then we don't only revert back to what we were before, but also we mess up a lot of things that are dependent on climate velocity. So it is clearly an important thing to keep thinking about. Yes.
Over here,
Yeah, thanks for your talk, Dan. I'm interested in your thoughts on whether and to what extent capacities for governance can be included in a robust assessment. It's hard for me to think about how an assessment can be robust without some representation of obviously under an SSP 585 scenario, global capacity for governance in the context of climate mitigation is clearly very low, right? As compared to a more of a peak shaving kind of scenario. And to what extent? So how does that get represented in the kind of scenario-based assessments that you're intending to incorporate?
Well, it's tough, right? And this is what I said at the beginning of sort of, do you do governance before, after, or during, right? To me, it's very positive to have countries at UNEA having this discussion, because the answer is that it's not up to me to figure it out, honestly. I think the worst thing we could do, and I was strongly, my first thing as the WCRP chair of that activity was to say, to tell the countries that it said the WCRP should do this assessment, not UNEA, which is like, no, I will never do this, because the point is that we can do the assessment with the coolest science we have, but if it is not perceived as legitimate, it's just gonna be pointless. So I think that we have to go through the pains of actually figuring out how to write the first assessment and have the countries decide what they want to do in terms of governance. It's not up to, example, for the ozone assessment, the parties to the Montreal Protocol explicitly asked, have a chapter on SAI. We wrote the chapter on SAI, they approved the chapter on SAI, the chapter is there, and they want to do it again. So eventually it just worked because the Montreal Protocols are a functional family, unlike the UNFCCC in many cases, right? I want the countries to say how they want the assessment to do. If UNEA needs to do the assessment and they want to have political scientists lead that because they think that governance is preeminent compared to science, do that. I mean, I feel like people have been hiding behind the fact we can't have an assessment until we have governance, we can't do governance until we have an assessment, and this circular thing has prevented a robust assessment. But I don't think we're gonna get it right the first time, that's why the feedback loop. But eventually, I think that a chapter in something like the IPCC or UNEA has to replicate some of the practices of the IPCC at large, so having working group 1, 2, and 3, thinking about physical science, adaptation measure, mitigation, and all of that. But it has to be, like, what I'm saying is that I can't figure it out, but if I would try the approach we haven't tried, which is let's just try to write one and figure it out as we go along, rather than let's not even start before we have a governance system set up in place. Does that make sense? Maybe not.
Well,
Shifty.
it does. I realize it's possible a governance system set up in place, but it seems to me you can incorporate questions and uncertainties about governance in the context of the modeling scenarios that you're addressing.
Yeah, and I think this is sort of where it would be impossible to do the assessment without some form of emulators that allows for larger exploration, because the whatever assessment gets made, you do the modeling before and then you do the assessment. So there's a lag in these things. But if a country wants to know what would happen to the Indian monsoon if there was this specific strategy because India were to deploy or the US were to deploy, these things are starting to happen in the literature and in the science. It's impossible to do that just by commanding people to do their own climate modeling. So having an emulator that allows people to sit down at a table and say, this is what would happen if you tried to cool a little bit, this is what would happen if you tried to cool a lot, this is what would happen if countries cooperated, this is what would happen if countries didn't cooperate. That is, to me, the way you sort of try to integrate the governance part. Not by having the scientists say, this is the simulation that we came up once in a meeting in a small room, and that's the only thing we're going to look at.
Thanks, Daniele. A quick question maybe. How do you see the climate model improvement process right now, and do you foresee that to change? As in, like, how fast does it go? Do we need to be faster in changing our climate models under various scenarios?
Yeah, that's excellent. So to me, two things. The first one is right now climate model improvement is tied to the FCC process. That's terrible, and I hope it goes away, and so do most of the climate modeling centers, because essentially you're catching up to these assessment reports, and so you have at one point you need to freeze the code, and then people are still trying to figure out what the difference between CSM1 and CSM2 are, and now we have CSM3. There's a constant catching up that I dislike. So to me, the main thing, and I brought a perspective earlier this year about it, is the fact that things should be a lot more transparent and say, we have this set of simulations that we will keep repeating. We'll stop pretending that we're updating our future projection all the times. We have this set of things, and then if we improve this thing in the model, here's our projections change. Here's how this uncertainty increases or decreases. The IPCC did that a little bit for equilibrium climate sensitivity in the past, but I wish this happened more. So to me that is, and for climate change it's kind of happening on another side, but for SRM, it's clear that you need different climate model improvements and you need different focuses, and so I wish that people were more honest in saying, look, the model that we use to explore SAI is going to look slightly different from the model that we use to look at climate change, because we need the stratospheric coupling, because we need more aerosol microphysics. And then we could use that to say, hey, we have this uncertainty, like there's this parameter that we've been trying to tune, and we don't know if it's 1 or 12. Here's this experiment that we could do in the outdoor that would allow us to narrow this down from this range to this range. And here's how we would go about improving the model if we do this experiment. And so this would allow us both to connect model improvement to projections and to say we're not proposing to do other experiment for the fun of it. We're to just go out and pretend we're having fun or launching balloons. We're doing it because we think this will help us narrow down uncertainty. So it's clear that they would need a different paradigm. And my hope is that by having the concept of an assessment, that a lot of people that are doing climate modeling that maybe haven't touched SRM yet will essentially get on and get in and start working together and sharing this idea to how to have these better modeling practices. I'll drag NASA into this, whether they want it or not. That's my.
Here. Oh, maybe go to Daniele for that.
All right, great talk, Daniele. I actually have a question sort of related to Dan's comment at the beginning. So it seems like you mentioned about this kind of empirical evidence or observational data is very important to kind of validate all the models. And obviously, a lot of the solar geoengineering work is based on modeling. So we need to verify, like, be confident on those modeling performance. But it seems like we probably don't have very good understanding about Pinot-Turbo, and then Pinot-Turbo might also not be a best scenario, like all the analog to SRM, because we're not injecting that huge amount of aerosols at one time as Pinot-Turbo. So we actually have some studies looking at smaller volcano eruption, and we find those compared to modeling just couldn't really reproduce like what we find on about these smaller volcano eruptions. So my question is, like, do you have any insights on kind of what kind of observational data are available or like are needed to better validate the model, like the community are using to assess these strategies?
Right, great. Yeah, so it is true that Pinot-Turbo is not the greatest thing, just what everybody's using, and in a way that's what we were starting with, but actually trying to use larger part of the records, trying to use Calypso a lot more actually a lot of the small volcanic eruptions, the problem is that sometimes maybe they happen at too high latitudes, there's a lot of cloudiness, and so the signal is harder, but that is absolutely fair as a thing. Now, when it comes to going back also to Dan's question and saying, sort of stressing out, these are all going to be imperfect. The point, a lot of things that we've been able to narrow down of uncertainties when it comes to climate change is because we've observed climate change. Like the IPCC going from maybe climate change is happening, but we cannot see it yet, robust, blah, blah, and now the last one being it's virtually certain that climate change is anthropogenic in nature. It's because climate change is happening, which is bad. But on the other hand, right, we can ask the same question about SAI. Yes, Pinot-Turbo is a terrible thing. And so what do we need to understand about our climate models so that if a small volcanic eruption happened, we have rapid responses that allow, we're still deciding on the protocol for the Hunga Tonga eruption that happened 2 years ago. Okay, and people are still arguing about what the protocol should be. And the answer is Hunga Tonga has zero effect on anything. But it's a clear example of the fact that you cannot wait 2 years, right? It's clearly a bad way to go. So we need a lot more of that. And when it comes to the improvements, it's also clear that, right, the volcanic eruption is going to tell you things at the mid to large scale, as in it's going to tell you about where the aerosols go, where the aerosols do at the end. But there's the smallest part of sort of what happens in the plume, what happens if you release the aerosols. There is no mixing, there is no subgrid mixing in the models unless you put it there for like the pluming grid work. Does that matter? What do we need? Again, I feel like one way to think about it that I think hasn't been outlined well enough yet, but is to say, what would we observe and learn on day one of a deployment that would allow us to say we were off track, or actually we're pretty good, or our models need to be changed in this way. So the off ramp that people sometimes talk a lot more about MCP. It is possible that there's also I've also seen some studies where small volcanic eruptions were very well reproduced in MPI and the fact that the aerosol distribution was actually pretty well reproduced. So I'm not that negative, and I think we should use that more, but yeah.
Right.
Awesome, thanks. I had a similar question to the governance one, but it's mostly been answered. So just like two small things about how the En-ROADS type simulator would work. One thing is, I wonder whether there's any principled reason for stopping at 2100. I know that's just how the models usually end at that point, but it seems like we might, situations in which we might do this for longer. And then the other question is whether you've thought about adding in a sort of, or maybe this is already in there, but a kind of moral hazard type scenario where we do in fact continue emitting while using solar geo and perhaps even adding in the sort of carbon removal implications of that sort of scenario.
Yeah, so I would say on the first part, well, the reason why we stopped at 2100 is that because the SSP stopped at 2100 and the emission scenarios from the integrated assessment models up to 2100 look very silly to be able to predict what emissions are going to look like. But there's work from a French group, CNRM. Suzanne Bauer has a couple of papers about this, sort of looking at the longer scale and what would how the carbon drawdown look like, for how long are you committing to do SRM? Great. Somebody also suggested that we add in the emulator. We had a couple of sessions with potential users for the emulator, and somebody did suggest, well, Pete Irvine suggested to add the moral hazard. I am a bit reticent to do that on this kind of the emulator, but I will say that we have a perspective that I've been working on with some social scientists that do this sort of human behavior modeling coupled to climate modeling to sort of try to understand this better and how would you add moral hazard, and more importantly, and Kate Rigg is also doing some really good work on this, how could you ever measure this moral hazard, right? Like what kind of experiments would you need to then tune your, I think that's a great, excellent part. And that the emulator kind of allows you to think about this much better and saying, look, this weird committee, this scenario MIP committee came up with these emission scenarios, and those are the only emission scenarios we're going to look at. So I think the emulator helps with that, because then having the emulator, the global version of this one already exists, is published, and it's in MATLAB, but we're working on, my student is an engineer, so, but we're working on having a Python version, and then people can couple to their own societal modeling version to try to explore these questions better for themselves.
So it seems to me that you're using model improvement in too broad a sense, and I worry that you're focusing on something that maybe the models will never do well, which is the magnitude of the response overall. I'd actually much rather understand across these different models how robust the regional effects are, which ones are reliable and which ones are not. Because I suspect that the mechanisms behind those, at least some of them, are pretty robust and therefore are pretty consistent, and we do a reasonable job of those. I suspect, for all sorts of reasons that you understand as well, that the magnitude of how much cooling you get for how many tons of sulfur or whatever other aerosol you inject is going to always be wildly uncertain. and until we even deploy it, and even then, it'll be a little bit of a surprise, and we'll adjust on the fly if we were actually operationalizing something like that. Frankly, what we really need is a better observing system that we don't have. We need that for climate anyway, and it would work for a solar geoengineering scenario as well. But what the models can tell us right now are some of the regional issues that are worth paying attention to. And I feel, even if we don't understand their magnitude, we understand their direction. And I feel like that's getting lost in your discussion of model improvement.
Yeah, fair. So model improvement means a lot of things. And I would say, again, even in the CMIP community, there's a lot of discussion about where do we go for improving the model, even for climate change. Do we add more processes? Do we add the direct representation of the carbon cycle? Do we increase resolution? Because you can't do both. And so the question a lot of people are having when it comes to climate change is, to get better societal information, do we just need to increase horizontal resolution in the models? There's ultra high scale resolution versions of a lot of models at 1 kilometer. They cannot be run for more than 6 months. Like, they take a month to run a month. So it's a bit complicated. So climate model improvements is a lot of stuff. And it's clear here, this is sort of the overlap between, yes, to resolve the regional, so let me put it this way.
I mean, so for example, some of the hydrologic effects in the Western Pacific over Indonesia, those are really important.
Yeah.
If we can be confident that we understand the mechanism and why the models are all doing this, and and that they're truly robust. That is, I would argue, more important than figuring out how big of an effect per ton of aerosol we put in. I think you're never going to get that right anyway.
I see what you're saying, but I would say that in a way I disagree, because when it comes to climate change, especially well-mixed greenhouse gases, it's easy to just frame the question of what would happen to a specific climatic system at 1, 1.5, and 2 degrees of warming, and how that would change. But when it comes to SAI, you cannot get out of the question of where are the aerosols? Where is the cooling happening from the stratosphere to the troposphere, and how is that affecting? We've seen it for monsoonal circulation in the system, in every simulation, right? That where you put the aerosols matters for the hydrological changes. So it is true that we can separate the question and say, where do we need to put the aerosols to have the aerosols? What happens when the aerosols are there on the energetics at the lower surface? And then are we understanding the process as well? Those are 3 things that one can sometimes separate, sometimes they're hard to separate, but they're all part. Climate model improvements, to me, in this figure, sort of includes all 3 of them. And then, of course, the prioritizing part it's important. But then the question is that, of course, the point is that we will never be able to tell. There's never a counterfactual for these things. Like, there's process level understanding also includes, do we understand the wormhole? Why are the models not having the correct SSTs, even for global warming? Does this matter? Because it affects tropical climate dynamics, right? There's a lot of connections there that are also important for climate change. So these 2, I don't only think of them in the stratosphere, but it is also true that in one hand, it's going to take us 40 years to figure out whether the monsoonal circulation is changing differently than what we expected to change under climate change that is not happening anymore if we're doing like the counterfactual becomes so much more complicated that there is a point where you say, well, but if in month 1 of a deployment, you're not just looking at the aerosols, you're looking at the radiative forcing, you're looking at the satellite-based products, you're driving your drones and measuring radiative forcing at the tropopause. And so then you can say, well, if we expect the forcing to be this much, that's going to be the cooling. Actually, like, I disagree with you a bit when you said that we will never know the cooling that well. I think that the cooling we will know pretty well, because we will be able to measure radiative forcing much better.
I meant from the models.
But we're going to need the models. What you will do at any time when you're doing SAI is that people will run the models, but not like we run them now in free running mode. They will sort of like, sort of in a forecast mode, driven by actual observations and reanalysis, and we will be able to tell, this is what's happening now with the aerosols, this is what we expect would have happened without the aerosols. So you're constantly, in that scenario, you need way better observation, but you also need a different paradigm of modeling that is a lot more closer to the detection attribution one, as I said before, in the sense that you're constantly running your model every day and saying, this is what we expect temperatures would have been without the aerosols, this is the temperature we observe. This is in 20 climate models. And then how, and 18 say a thing, 2 say another thing. Why do these 2 models say a different thing? We're not even close to, I don't think we think enough, since we're worried that this is gonna help manifest SRM into existence. I don't think we talk enough about how would it actually look like? How would a world under geoengineering look like? Holly Buck, who's here at Harvard this year, has this wonderful book called After Geoengineering I love. And it's the perfect example of her thinking, how would the world and societal relationship in science look like when it comes to this? And I think this would help us to think about what kind of models do we need to do the detection attribution that would be necessary to figure out whether we're doing things right or wrong.
It's 1:30, so we have the room for another half an hour or so feel free to go on Daniele. He's probably pretty hungry too, but let's give one more round of applause. Thank you very much.